All right, so this is Math372, Complex Analysis, Lecture 24. So the goal for today is to continue our study of Fourier analysis, building to Poisson summation. And the reason we're doing this is we need Poisson summation to have a good analytic continuation of the Riemann zeta function. We have a cheap continuation for real part of s greater than 0. But for a real attack on the primes, and I hope some of you might take Professor Goldmacher's class in the spring, you need a lot more. So there's many different techniques. Poisson summation is a great one. The other benefit of this is it's going to prove a lot of theorems along the way that are just useful for other things in mathematics. So in addition to the clock falling today, there seems to be shading issues and whatnot, and so trying to figure out how to adjust things so that the blackboard is somewhat visible. All right. Okay, so I have put on the file board over here a quick review of the terms. So the Fourier coefficients f hat of n is the integral from 0 to 1 f of x e to the negative 2 pi I n x. E n of x is e to the 2 pi I n x. The Dirac kernel and the Fourier kernels are defined thusly. We saw our old friend the geometric series here again. We can write this as e to the 2 pi I x to the nth power. And then by using the geometric series and doing some algebra, you should be able to get it to equal this. And then to get the Fourier series, we just do a similar analysis. And we now sum these Dirac kernels. And after doing some analysis on sums of sines, we end up with a nice result. Now, how should we be able to get something like this? Well, we can write sine as a difference of two exponentials. And then we can play the geometric series game all over again. The nice thing is the denominator is all the same. So this is just a good algebra exercise to go through and verify that these are correct. It turns out these kernels have very different properties. So if you look at the Fourier kernel is extremely nice. It's non-negative. You've got sine squared over sine squared. It integrates to 1. And most of the mass is concentrated near x equals 0. So if you look at what's going on, when x equals 0, we have 0 over 0, so we have to use L'Hopital. So we use L'Hopital once, we'll get 2 sine x cosine x over 2 sine, so this is maybe not a pleasant L'Hopital to do. But we could also do Taylor series expansions. Near x equals 0, sine of x looks a lot like x. So when x is extremely small, the numerator here looks like n pi x, so it will look like n squared pi squared x squared. The denominator will look like pi squared x squared. So the pi x cancels, and we'll have it looking like n pi x. So when x is really small, this is going to be inflating a lot. So most of the mass of this is going to be near x about up to size 1 over n. Okay? This one over here is both positive and negative. And that's going to cause things to be a lot harder to work with. So there's a bunch of calculations that we're going to need. I'm going to leave a lot of them to you to just do. So the Fourier series is SNF of x is the sum, n goes from minus n to n, f hat of n, e to the en of x. I'll just write it like that. So what we're essentially doing is we're looking at a decomposition of f in terms of our basis. And the hope is that this basis is complete. We know the basis is at least orthonormal. It turns out that this is also equal to the integral from 0 to 1 of f of, I'm using f of t dn of x minus t dt. So this is called a convolution. We often write this as f star dn at x. You can also view this as an integral transform. I start off with the function f, and I get a new function out of this. And the new function is going to be a function of x, and the x dependence is here. I'm integrating with respect to t. The t is occurring in both parts. Okay, so you give me a function f. This is going to give me a new function Sn of f. Okay, we often call this part over here the kernel. And so the kernel is going to be a function of two variables. Here it's a function of x and t. What's very nice about this kernel is it only depends on their difference. In all of the stuff we're doing, we're always assuming f is periodic. And if f is not periodic, we talked last time how we can just reflect it, and now we've made it periodic. So that's not really a big assumption. The Fourier series, Tn of f, the reason we use the letter T is it's the letter after S, is a weighted Fourier series. It's the sum, n goes from minus n to n, 1 minus absolute value of n over big N, f hat of n, En of x. Any thoughts what this might be the convolution of? Yes, yeah. The Fourier series is probably the convolution with the Fourier kernel. So this is just going to be the integral from 0 to 1 of f of x, fn. F of t, fn of x minus t dt, and this will just be f star fn of x. So depending on what we convolve with, we get slightly different series. What's nice about this series, now I'm actually trying to remember, is it actually absolute value of n over n, or is it the squares? Might be squares. We'll have to do the calculation. I can't remember now if it's squares or not. It doesn't really matter, because the point is that as this is getting larger and larger and larger, then this fraction is approaching 1, so this is then 0. So it's a smooth cutoff. And one of the big themes is that smooth cutoffs are a lot easier to work with. So the way you would prove all this is you would just do brute force integration. So if we wanted to prove something like this, if we look at the integral from 0 to 1 of f of t dn of x minus t dt, this is the integral from 0 to 1, f of t, and now dn is going to be the sum, n goes from minus n to n, e to the 2 pi I n, and now I evaluate it at x minus t dt. What would I love to do right now? I'd love to interchange the orders. Am I allowed to interchange the orders? So can I interchange the orders of summation and integration? What do you think? What's the danger when you interchange? Why do you have to sometimes be careful? It's infinities. This is a finite integral. This is a finite sum. Finite, no problem. We can interchange without too much trouble. And this is now going to be the sum. N goes from minus n to n. The integral is 0 to 1, f of t. Now I'm going to write this exponential as e to the negative 2 pi I n t dt. And I have an e to the 2 pi I n x. Well, this is just my definition of the Fourier coefficient. So it's the sum, n goes from minus n to n, f hat of n, e n of x. And that's what we wanted to show. So now we could go through and we could do a similar argument with the Fourier kernel, and that would resolve if it's absolute value of n over big N or the square of that. Okay? So what this tells us is that if we want to get to the Fourier series, there's a really nice way of getting to the Fourier series. All we have to do is understand this integral. Now, just because I write something down does not mean that this is an integral that I can do well. You will not remember this integral from Calc 1, 2, or 3. This is not something you would look at. This involves a large sum of exponentials. Exponentials are highly oscillatory. We do not want to have to evaluate this term by term by term. The reason we can make progress with something like this is if you look, oh, it's a good day, it's moving. If you look at what is the Dirichlet kernel, oh, nice closed form expression. Let's just integrate directly. If you look against the Fourier kernel, oh, again, nice closed form expression. So the hope is that we can now say, look, our Fourier series or our Fourier series is equal to this integral convolution. And the kernel for that has a nice closed form expression. And now we just have to handle that one integral. it's not something you would have seen in your earlier calculus classes, but it's not an unreasonable thing to look at. And so there's hope. Okay? So there's a lot of various things we can start to look at. Right, are we all comfortable on this? We're basically doing subsets of an entire course on Fourier analysis in about a week. So the goal is to do just enough to get to Poisson summation and some other nice results along the way. So we will not prove when the Dirichlet kernel gives pointwise convergence. But we will prove when the Fourier series gives you pointwise convergence. Okay. So natural questions, of course, to ask is, how close are these approximations to our original function? The hope is that as n gets very, very large, this gets closer and closer and closer to our function, at least if our function is nice. Maybe if it's differentiable a couple of times. The Fourier series might even converge a little bit better under weaker conditions because we have some kind of smoothing going on. We have smooth cutoffs rather than sharp cutoffs. So the first question is, how close is Sn of f to f? And so one of the questions to look at is, how do we want to measure closeness? So this is a chance to review some concepts from real analysis, or if you haven't seen them, at least introduce them. If you have taken measure theory, you may have seen some of these. If you are going to take measure theory, you will see these. If you're going to graduate school, you will almost surely have to know these things to pass qualifiers. How many of you have not seen LP spaces? Okay, so everyone else has seen LP, so about split half-half. So we say LP of a set S is equal to the set of all functions f such that the integral over S of f to the pth power is less than infinity. So we will frequently look at functions that are either L1 or L2, and typically we'll look at functions on 0, 1, or minus infinity, infinity. So for instance, L1 of 0, 1, and technically I should probably put this in square brackets here to say it's of the interval, would be the set of all functions f such that the integral from 0 to 1 of f of x dx is finite. L2 would just be the same with this replaced with now squaring. So natural questions could be, which is a stronger condition? To tell you the function is integrable, or to tell you the function is square integrable? And does it matter if we're looking at 0, 1, or if we're looking at the interval minus infinity, infinity? So which do you think? Let's have L1 of 0, 1 versus L2 of 0, 1. Do you think one of them is included in the other, and if so, which way? So if I tell you the function is integrable, is it square integrable? If I tell you it's square integrable, is it integrable? Or maybe there's some things in L1 that aren't in L2, and there are some things in L2 that are not in L1. The worst talk I think I've ever heard in my life was a talk about functions such that f log log f squared is in L2, something like that. A really small technical change and weakening. And that's when you know I'm stuck here for 50 minutes. Hopefully, do I have some homework to grade? Oh, good, I do have homework to grade. Excellent. So you never go to a talk unprepared. All right? Any thoughts as to which is a stronger condition on 0, 1? Being integrable or being square integrable? So you think if you're square integrable, you're integrable?
Usually, except for 1 over.
All right, so let's take a function that blows up. So give me a function that blows up, but is integrable.
1 over x is integrable in some places.
Well, 1 over x is not integrable in 0, 1. So give me a function that's close to 1 over x that's integrable.
1 over x squared.
No, 1 over x squared, you're going in the wrong direction. 1 over x squared is not integrable.
Right. Okay.
So 1 over square root of x would be. So we take 1 over square root of x. That's integrable on 0, 1. It blows up, but it doesn't blow up too badly. If I square it, I get 1 over x, which is not integrable. So I could have something that's in L1 that's not in L2. Okay? So do we all agree that there's at least one function in L1 that's not in L2? So which condition do you think might be stronger to say you're in L1 or you're in L2? Yeah, so maybe if I tell you you're in L2, that's a stronger condition. And so here's a really nice observation. F of x is less than or equal to f of x squared plus 1. If f is greater than 1 in absolute value, then f of x squared is greater than f. If f of x is less than 1 in absolute value, then it's less than 1. So the absolute value of f is less than or equal to the absolute value of f squared plus 1. And because our interval has finite length, if I now integrate from 0 to 1 of the absolute value of f, that'll be less than or equal to the integral from 0 to 1 of absolute value of f squared plus the integral from 0 to 1 of 1. So if you're in L2, this side is finite, and you're in L1. So anything in L2 is in L1. But there are some things in L1 that are not in L2. So did I do this right? So if you know your function is square integrable on 0, 1, it's also integrable. Would this argument work if we looked at, instead of 0, 1, if we looked at the interval minus infinity, infinity? Then the absolute value of f is still less than absolute value of f squared plus 1. But now we're integrating this from negative infinity to infinity. And now this gives us an infinity. And then this tells us, well, the L1 norm of f is at most positive infinity. This is not that useful. So it's essential here that we have a finite interval. So if I tell you your function is in L2, it's also in L1. If I tell you the function is in L1, it may not be in L2. Okay, so if you know your function is square integrable in 0, 1, it's also integrable in 0, 1. Okay, so we're comfortable with just a brief introduction as to what LP spaces are. So these are extremely useful. L2 is actually one of the most useful spaces there is because you can actually put a dot product on it. So it's always a challenge as to exactly how much to tell you to keep things interesting. All right, so let's talk about how close is Sn of f to f. Well, there's a couple of ways we could measure this. We could measure it point-wise. At each point, how close are they? And let's look at the largest difference. We could also look at the integral of the difference, or the integral of the square of the difference. And if you've done any statistics, if you've seen method of least squares and all the different ways of measuring error, it's very similar to that. How do you want to measure error? If you think about it, if the L1 or the L2 norm is small, it means most of the time you're close. So maybe you could be off by a little bit at a few points. Now, there are dangers. This is a rich subject. I'm trying to just give you a sense of where things go so you can decide what you might want to look at in the future. It's called the Gibbs Overshoot. You can take a function which is, say, -1 here and +1 here, and maybe we'll define it to be 0 here. And when you look at the Fourier approximation, it shoots down like this, then shoots up, and it overshoots by about 18%. And so the convergence at this one point is really bad. However, what's happening at this one point? What's true about the function? It's discontinuous. So the function breaks down. It's not surprising that things break down. I would have much preferred if it kind of went nicely like that. But it actually overshoots in a fascinating way. So this is the Gibbs phenomenon. He was one of the first American scientists of note. Basically spent his entire life at Yale, New Haven. Have definitely visited his grave several times. Phenomenal You might have seen them in statistical mechanics. A lot of our stuff in vectors comes from Gibbs. So for the most part, this is a European course in terms of essentially Cauchy, Riemann, and a few of their friends. It's nice when some Americans eventually get into the game. As you get into the more modern results, then you will start getting people from all over the world in terms of where things are going right now. All right, so let's look at maybe Sn of f minus f squared. Integrate this from 0 to 1 and see how large is that. So I'm going to write this as a dot product. This is equal to Sn of f minus f dotted with Sn of f minus f. And when you go through things, this is Sn of f minus f Sn of f, Sn of f. It turns out that's going to just be twice the same thing. I believe twice Sn of f plus ff. And now when we go through things, we take the dot product of Sn with itself. That's going to just be the sum, and it goes from minus n to n of f hat of n squared. When I look at what's going on over here, if I look at Sn dotted with f, well, all that's going to matter is when I integrate this against En, I'll just get back f hat of n. So I'm essentially going to get back the same thing twice. So I will leave the calculation to you minus twice sum, and it goes from minus n to n f hat of n squared plus ff.
When you're taking the dot product of Sn of f with itself, is something nice happening to the E coefficient that makes it go away?
Well, yeah, because when I take the dot product with f, for each one of these, that's just going to give me, again, f hat of n, or actually the complex conjugate maybe of f hat of n. And so I'm going to get essentially the same sum again.
Okay.
So you should go through and you should, put in the details for these arguments and do these products.
Okay.
So when you just take the dot product of this, just very, very briefly, Sn of f dotted with f, you'll get a sum of f hat of n En dotted with f. But En dotted with f, this is just the complex conjugate. And so I'll just get f hat of n bar with the sum over n. And so that's where this is coming from. And so what we get at the end of the day is we get the L2 norm of f minus the sum, and it goes from minus n to n of f hat of n squared. Now, what do we know about this integral over here? What can you tell me about that integral?
It's also an L1.
If it's finite, and so our integral will be, well, we've shown that it's finite. What can you tell me about its value? And it can be a trivial observation. What do we know about this integral?
It's positive.
Almost. So close. Off by epsilon. Non-negative. It could be 0, right? Maybe f is just E1 of x. Maybe it's a perfect fit. It's possible. Unlikely, but possible. So we know that this is non-negative. So if that's non-negative, this expression here must be greater than or equal to 0. So you get 0 is less than or equal to the L2 norm of f minus the sum, and it goes from minus n to n of f hat of n squared. So if we bring this over to the other side, this is called Bessel's inequality. The sum, n goes from minus n to n of f hat of n squared is less than or equal to the integral from 0 to 1 of f of x squared dx. How However, you can improve Bessel's inequality. How can we improve this? So I have a sum from minus n to n of f hat of n squared. What could I sum over instead? So this is true for each n. I can take the limit as n goes to infinity. Right? For every n, this sum is less than or equal to this. Let it go to infinity. So also you get the sum, n goes from minus infinity to infinity, of f hat of n squared. And this gives us a lot of information. It means the sum of the squares of the Fourier coefficients converges. Therefore, f hat of n has to go to 0 if f is in L2. That's nice. The Fourier coefficients go to 0 even if f is just in L1, but it's more work. We can get this with very little work. I prefer the very little work. I'm happy to make some slightly stronger assumptions about my functions. At the end of the day, we'll be using this on Gaussians and stuff like that. No problem at all with decay, no problem at all with continuity and differentiability. The goal is not to have the most general result possible now. The goal is to get to Poisson summation and some interesting stuff along the way. This proves the Fourier coefficients tend to 0. Good. If I'm trying to represent something as an infinite sum, I kind of hope my different directions are going to 0. If not, there's no chance of convergence. Right? So a necessary condition for something to converge is that as you go further and further and further out, the contributions are getting smaller and smaller and smaller and smaller. So this gives us hope that there could be a nice theorem coming. It's not a proof yet, but at least it gives us a chance. Okay? So the Fourier coefficients are going to 0. If you could, how would you love to tweak this relation? What would you love to replace this with? So one possibility is strict less than, but if it's strict less than, I don't know exactly how they differ.
You mean like add in the difference and then...
Well, so the question is, what's the difference between this and this? What would you love that difference to be? 0. So actually, they're equal. And what this tells you is certain infinite sums can now be reduced to an integral. In some sense, this is the opposite of what we've been doing in complex analysis. We've been reducing integrals to finding a residue, which is looking at one term in a Taylor series expansion. I feel compelled to show you that life actually can go in the other direction. And you can actually convert sums to integrals. What does this mean? If this is an equality, all I need to do then is choose a function whose Fourier coefficients squared are what I want to sum. So for instance, the sum of 1 over n squared. If I can find a function whose Fourier coefficients are 1 over n, and I can integrate the resulting function f, I'm going to be able to sum 1 over n squared. So how many of you have seen this proof? Okay, good. So we're leading up to something you haven't seen before. You should know the sum of 1 over n squared is pi squared over 6. We've seen why this is important. We're leading up to that. We just have to find a nice function and find its Fourier coefficients. So it'll turn out that the function we look at will either be something like x or something very simple like that. It'll be an easy function to work with. The integral won't be that bad. I will still make algebra mistakes on the board, don't worry. But they'll be easy to find. Okay, so I hope you're beginning to see the power of this. Is the clock still working roughly? Excellent. Okay.
No.
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 It's like 8:01.
It's 8:00. Wow, we've gone back in time. Excellent. I know in 2015 I gave a Back to the Future lecture because I think I had class on the Back to the Future day when Marty McFly travels. And so that was a very fun lecture to give. All right, so we have plenty of time today. This is wonderful. Excellent. We will be able to actually prove everything. So one thing is, how do we actually prove something like this? Well, let's look and see where was the challenge. It's essentially this difference, right? So if you want to look at what's going on, we basically have SNF minus F, SNF minus F, plus the sum, n goes from minus n to n, f hat of n squared equals the integral from 0 to 1 of f of x squared dx. Now we want to take the limit as n goes to infinity. So when we take the limit as n goes to infinity, what we need to do is we need to just show that this goes to 0. If we can show that this goes to 0, then this will actually equal that. So here's the way to prove Bessel's inequality is Bessel's equality. Is you show that the Fourier series converges to the original function in L2. Okay? And then, again, part of this is I'll send you an email. You either email me directly or email me using the anonymous email account as to how much detail do you want to get into stuff like this. I'm happy to give you full proofs. I'm happy to just mostly prove things and say, we just have to show this goes to 0. This is roughly what goes on. You can somewhat bypass this by, instead of using the Fourier series, what could we use? Instead of using the Fourier series, we could use the Fourier series. And then all we would have to show is the Fourier series goes to 0. We would have a weighted sum, but the weights would be 1 minus, like n over big N. And those weights would all go to 1. So we can actually prove this just by using the Fourier series and not going through the Dirac series. So similar result for a Fourier series. And then if we just go through that approach, it's a much easier calculation. Okay.
Are those two fundamental in some way, or are there many variations one could concoct?
There are many variations one can concoct. That's an excellent question. These ones are particularly nice because they have closed form expressions for the kernels.
Okay.
So in fact, what we're going to do is, if I could have planted a question, that would have been the question I would have planted. So what we're going to look at now is approximations to the identity. So for those of you who have taken physics, this is essentially a rigorous approach to what is a point mass. They sometimes call this the Dirac delta functional. So we say A is an approximation to the identity if the following is true. A of x is greater than or equal to 0. Actually, we'll do a sequence of functions. A of x will be an approximation if each one of them is greater than or equal to 0. Each one of them minus infinity to infinity of an of x dx equals 1. So they always integrate to 1. And the last one is for all epsilon, do this way. For all delta greater than 0, the integral over x greater than delta of an of x dx goes to 0. So what this is saying is here's 0, here's delta, here's minus delta. As n goes to infinity, the probability you're in either of these extremes is tending to 0. So that as n gets very, very large, all of the mass is essentially being concentrated between minus delta and delta. Okay? It turns out the Fourier series is an approximation to the identity. The Dirac series is not. Dirac series is sometimes negative, so it clearly loses out on this. The Fourier series, you can clearly look at it, it's non-negative. Integrates to 1 is not so bad. The harder one is that the approximation, if you stay away from 0, it's negligible. Now I'm writing this on the interval minus infinity, infinity. You could, of course, do this on the interval 0, 1. You could do this on the interval minus a half. If we're doing things with Fourier series, we might want to do minus a half so that the key point is not at an endpoint. If we do 0, 1, then you would go from 0 to delta, and then you'd go from 1 to 1 minus delta. That would be the interval where most of the mass would lie. So it's just more convenient to just shift things and go from minus a half to a half. It turns out that if you have a function which is non-negative and integrates to 1, you can form an approximation to the identity. So imagine b of x is greater than or equal to 0, and the integral from minus infinity to infinity of b of x equals 1. Let's let bn of x equal b of nx of n bn of x. Clearly, bn of x is still greater than or equal to 0. The second one, if I now integrate from minus infinity to infinity of bn of x dx, this is the integral from minus infinity to infinity of n b of nx dx. Let u equal nx, let du equal n dx. And so when you do that, you see that this is just the integral of b of u, which is just 1. So each of the bn's satisfies property 1 and 2. And now what we just need to do is we need to show that they satisfy the third property, that most of the mass is going to be very close to 0. Well, our function b is integrable. So how much mass must you have as you go far and far away from x equals 0? The mass must be going to 0. And so because I have an n here, once x is of size 1 over n, we're already at 1 unit from the origin. When x gets to 1 over square root of n, we're root n away from the origin. So just as a quick exercise, let's integrate absolute value of x greater than or equal to 1 over square root of n of n bn of x dx. We'll see if this is enough to work. Well, this is, if I let u equal, oh, I'm sorry, it's b n x, sorry. If I let u equal nx, du was n dx. And so now, if x is greater than or equal to 1 over root n, how large is u? U will be greater than or equal to square root of n. And we'll just have b of u du. But because b is integrable, we know that if you just integrate b in the extremes, it goes to 0. So this has to go to 0 as n goes to infinity, as b is integrable. If you want, for any epsilon, you can find a big B, can't use B. You can find a C such that if you integrate from minus C to C, you have 1 minus epsilon of the probability. And then we just take n so large. So what this tells you is you have a huge source of approximations to the identity. Take any non-negative integrable function that integrates to 1. If it doesn't integrate to 1, not a big deal. Just rescale it so it integrates to 1. Any idea what's a really good family of approximations to the identities? What is a good choice for B? One over what? I mean, I want a function that's really nice. So a function, I want a function that has probably great decay, very differentiable. Gaussian, right? Often use Gaussians. So what I want to do now is I want to quickly show that the Fourier series is an approximation to the identity. And the theorem, and this is why your question was the perfect question, is if you have any approximation to the identity, it will converge to the function. And since the Fourier series is an approximation to the identity, it will then converge. So we actually get the results very nicely. All right, so I think I have not made any algebra mistakes yet. This is, got about 10 minutes to go. So Fourier kernel gives an approximation to the identity. So recall, dn of x was the sum, n goes from minus n to n of en of x. Fn of x was 1 over n, the sum n goes from 0 to n minus 1, dn of x. And we said that this was sine squared n pi x over n sine squared pi x. All right. Non-negative. Yes. Next one. Integrates to 1. Well, if you look at dn of x, if I integrate dn of x from 0 to 1, what's the only term that has a non-zero integral when I integrate dn of x? So remember, these are all sines and cosines. If n is not 0, dn of x integrates to 0, right? So the only term that contributes for dn of x is when n equals 0. So if I integrate from 0 to 1 of dn of x dx, this is the sum, n goes from minus n to n, of the integral from 0 to 1, e to the 2 pi I n x dx. The only contribution is when little n equals 0. So each of the dn's always integrates to 1. So when I integrate this, each one of these integrates to 1. I have n of them. I then divide by n. It integrates to 1. 2 out of 3. All right, this is meatloaf level. Let's do a little bit better. Right? Now we need to show small away from 0. At some point, it would be nice to use the sine squared. Right? We've used it already a little bit in proving that it's non-negative. And the Fourier kernel is different from the Dirichlet kernel in that regard. The Dirichlet kernel is negative in places. But this is the place where we're going to really use it now. Let's integrate x greater than delta of fn of x dx. So we need to just show that there's negligible mass away from 0 as n goes to infinity. This is going to be the integral x greater than delta, or actually by symmetry, I'll go x goes from delta to a half and then multiply by 2. And I'll have sine squared n pi x over n sine squared pi x dx. Okay, now let's look at the bottom. As x goes all the way up to 1/2, this becomes the sine of pi halves, which goes to 1. So the worst case for us is when x equals delta, right? So this will be less than or equal to 2 over n, 1 over sine squared pi delta. And now we have the integral from x equals delta to 1/2 of sine squared n pi x dx. Can anybody bound the integral of sine squared?
1.
Yeah, it's bounded by 1. You could actually even bound it by a half if you want, because sine is at most 1 in absolute value. So this will be less than or equal to 1 over n sine squared pi delta. And now what you see is for fixed delta, let big N go to infinity. So fixed delta, N goes to infinity, goes to 0. We have now shown the Fourier series, the Fourier kernel is an approximation to the identity. Okay? We are sadly so close. It would be wonderful to just say, well, it's not quite 10 o'clock yet, so we still have plenty of time. We've got 4 minutes left. So let's see if we can do it. Approximation to identity of a continuous function converges to the function. All right. So let's look at f star an of x. This will be the integral from minus a half to a half f of t an of x minus t dt. So this is what we're going to do. We will use this for the Fourier series, but of course we could do this for any approximation to the identity. All right? Well, we want to compare this to f of x. What do I love to do? And I know I'm going to lose time by saying this. What is my favorite things to do mathematically? There's 3 things. Multiply by 1. F of x is the same as the integral from minus a half to a half of, let's see, how do I want to do this? F of x an of t dt. Right, because the integral of an of t dt is just 1. This is a approximation to the identity. It integrates to 1. F of x is constant. I pulled that out. This is just 1. It turns out convolution is commutative. I can write it, it's also minus a half to a half of f of x minus t an of t dt. Just do a change of variable at u equal x minus t. So I'll leave this to you to prove that this is the same as an star f.
Is this why we... I'll wait till you finish.
Okay. So somebody be watching the time, and when it gets too close to you have to go, let me know. We will probably have to stop in a moment. I now subtract these, and I can get f of x minus f star an of x. What's the difference? That's going to be the integral from minus a half to a half of f of x minus f of x minus t an of t dt. When t is close to 0, this should be small because it's continuous. When t is away from 0, so because my function is continuous, it's bounded. So I can write this as, the integral, say absolute value of x is less than delta, f of x minus f of x minus t an of t dt plus the integral x greater than or equal to delta of f of x minus f of x minus t an of t dt. For this part here, because my function is continuous, my function is bounded. So this integral here will be less than or equal to maybe twice the bound on my function, and then the integral x greater than or equal to delta of an of t dt, but that goes to 0. Okay? Oh, I've got about 12 seconds left. Okay? So this part goes to 0. For this part over here, what we now do is by continuity, this is going to be at most epsilon, and then the integral of this is going to then be 1. And so now, this part over here, this part is less than or equal to epsilon by continuity, so in absolute value it's going to be less than or equal to epsilon than the integral of x less than or equal to delta of an of t dt. But we can extend this to less than or equal to 1/2 at no cost, and because this integrates to 1, we're done. All right, so this was a little bit fast. I'm happy to review this a bit at the beginning of next class, but this gets us to the point where we've proven approximation to the identities converge pointwise if the function's continuous. And so now on Friday, we're going to just get consequence after consequence.